Oh, hi, I didn't see you there. Thanks for stopping by the Econ building. Well, I mean, since you're here, we might as well do a crash course in Econ 388, Introduction to Econometrics. I mean, why not? All right, first of all, let me take this jacket off. Kind of hot in here, actually. Okay, well, this is a very dense class. There's a lot of material to cover, so let's just get right into it, okay? And by the time I'm done, I hope you feel like you got hit by a bus of econometrics in a very survivable way, okay? So let's start with our econometric process, okay? Econometrics uses data to answer causal questions, okay? That's the whole purpose. That's why we're here, to isolate causality, all right? There's different types of questions. There's correlational questions and there's causal questions, right? A correlational question might be, how does ice cream consumption in a city relate to murder rates in the same city, right? Those things, if you drew a graph, those things might move together. Ice cream consumption and murder rate in the city. But it's a very different question to ask, how does consuming more ice cream affect the murder rate in a city? See, that's a causal question. That's a very different type of question. You can't really answer that by drawing a graph. You got to do a lot more, well, econometrics to answer that question. And so that's why we're here, okay? So imagine a universe in which there's our world and there's a world of demons, okay? And the demons want to come into our world, and the only way to stop them is through the power of music, all right? So let's say we have all these stars, these pop stars. Let's say they're K-pop stars, and they have a dual commission. Their job is to sing K-pop and to hunt demons, all right? Pretty simple job. They just got to make sure they do both. And one of these demon hunters, her name is Zoe. And Zoe wakes up one day and she says, hey, I think that wearing makeup actually helps me kill more demons. I wonder if that's a causal relationship, okay? So Zoe's asking a causal question. She's wondering, and specifically she's gonna measure this in how much she spends on makeup. And she's gonna say, does that really help me kill more demons? And so she is starting with a question, okay? The econometric process starts with a question, just like that. And in order to answer this question, Zoe would like to make a model that she believes, relates demons killed to money spent on makeup. So she's going to assume this linear model, okay? Yi is the number of demons killed by a demon hunter, okay? It's going to be some intercept, and it's going to be some linear relationship to xi. And xi is going to be the amount spent on makeup. And then it's not going to be perfect, so there's going to be other factors that affect demons killed, so we'll call it an error term for every individual. And that's her model. And with her model, she's actually assuming something very specific. She's assuming that the expected epsilon given x is actually just the expected epsilon. In other words, epsilon is not dependent on x. The error term, the other things that affect how many demons someone kills, is not dependent on, the things that affect how many demons are killed are not also correlated with makeup spending, okay? So we can easily make that 0, okay? But the core of this assumption is that epsilon and x do not relate to each other, okay? Makeup spending, there's nothing that affects both demons killed and makeup spending. Okay, that's a very important assumption. We call that the zero conditional mean assumption. We also refer to it as the assumption of exogeneity. Okay, our x's are exogenous, okay, as opposed to endogenous. So, all right, let's see. Okay, she's got her model. She's got her conditional mean assumption. She does need some data. So she's going to collect a data set, and this is going to be a cross-sectional data set, okay? In this data set, she's going to have a bunch of demon hunters, and let's say they're all over the world, okay? All kinds of demon hunters all over the world. She's going to have data on the demon hunter, how many demons they kill in, let's say it's over a month, okay? How many demons they kill that month, and how much they spend on makeup in that particular month. Okay, that's all the data she needs. And she's got herself a cross-sectional data set right there. And now she has her question, she has her model, she has her cross-sectional data. Now she just needs to estimate the effect of makeup spending on demons killed. How's she going to do that? She's going to use something called OLS, ordinary least squares. What does OLS do? Well, let me just draw a little picture for you, picture of your regression. So you're going to have your data set. All right, she has these lines scattered. Here's your makeup spending, here's your demons killed. Okay, and she has a bunch of data. Those are all her dots right there. And she wants to draw a line of best fit through this because she assumes it's a linear relationship, okay? And so how mathematically does she draw her line of best fit? Well, for starters, if we look at a particular observation, we see that that observation can be combined into a couple things. There's the part that's explained by your line, okay? We're going to call the line y hat, okay? We're going to say that y hat, that's your predicted value, the value predicted by your line for an individual, is going to be, so the betas are Greek, just like the real Greeks, we'll never know them till the next life, okay? So we got beta hat 0, that's your estimated beta naught, plus beta hat 1x for that individual. And there you go, that's your line right there. Y equals mx plus b, except we use some different letters, but that's essentially what that is. So part of this is explained by your line. We're going to call this part y hat, okay, for that particular individual. And now we have some extra part right here, okay? That is our estimate of the error term. We're going to call that our residual u hat for that observation. Okay, so we've broken this up into our predicted value and our residual, all right? And mathematically, to draw the line of best fit, this is what ordinary least squares does. It takes the arguments, all right, and it chooses beta naught, and it chooses beta 1, or b naught and b1, the arguments that minimize the sum of your squared residuals, okay? That is ordinary least squares, okay? And we did define our residual, or I guess we can define our residual, just to make things super clear. That's going to be y, the actual value, minus y hat, the predicted value, okay? What's left over is the residual. So if your y is wider than your predicted value, you can have a positive residual, and vice versa, okay? So that is what she's going to do with OLS. Now, we could go through and we could actually do the calculus, and we could derive these and everything. I'm going to keep that for a different resource or a different video. This one's going to be plenty of content by itself. But suffice it to say, here's the punchline, that we end up with beta naught as, and this is our OLS, our beta hat naught, is going to be y bar minus beta hat 1 x bar. Okay, that's the formula for that. And our beta hat 1 is going to be the covariance of x and y, that's the sample covariance, over the sample variance of x. Okay, these are our OLS estimates. Okay, perfect. Now we have our OLS estimates. We're really close to being able to do inference, all right? We just need to take our data, our estimation, we need to calculate those, and then we can do inference, okay? Let's see, what else do we need before then? Well, let's just start by calculating these, okay? So let's say our x bar is 5, and this is in thousands, so that means that the average spent on makeup in a month by your average demon hunter is going to be $5,000, all right? And then our y bar, average demons killed in a month, is going to be 12, okay? So, all right, we got those. Let's see, our variance of x, let's say that is 4, and let's say the covariance of x and y is 3.2. All right, so we have all of these numbers, and we now have what we need to calculate beta hat naught and beta hat 1. So let's do that. We start with beta hat 1 because it's, in beta hat naught. So beta hat 1 is going to be, let's see, the covariance of x and y is 3.2 over the variance of x, the sample variance, rather. Yeah, that's going to be 4. So beta hat 1 is about 0.8. Well, it is 0.8. And then beta hat naught is going to be y bar minus beta hat 1 x bar. So that's going to give us 8. Okay, and there we go. That's our OLS estimates. So we know from this data set and our OLS estimation that beta hat naught, that's going to be our, that's going to be basically when xi is 0, when, for a demon hunter that spends $0 in a month on makeup, they're going to kill 8 demons. All right, and for every extra $1,000, every extra $1,000 that they spend on makeup, then their demons killed is going to go up by about 0.8. All right, cool. That's our OLS estimates. But are those significant? That's my question. Like, how strong are these estimates? Well, in order to find that out, we actually need to know the variance of beta hat 1. Okay, this is going to help us do our estimation. So the variance of beta hat 1 is going to end up being the sigma hat squared of epsilon. That's your variance of your sample variance of epsilon. Okay, that's going to be over your let's see. I'm going to call this SXX. Okay, and SXX, I'm just saying, like, that's just a name for the sum of your deviations from the mean for x. Okay, something like that. It's very close to the variance of x. I mean, if you added like 1 over n minus 1 there, you would get the variance of x, right? So you could also think about this or write this as the sample variance of epsilon over, n minus 1 times the variance of x. That would be another way to write that. I kind of prefer writing it this way, so we'll just stick with that. So this is the variance of beta hat 1. And what is the sample variance of epsilon? How do you even get that? Well, that has its own thing, okay? That is going to be, I'm kind of running out of space here, that is going to be the sum of your squared residuals over n minus k plus 1. Okay, there you go. So that's how you get that. And we know about SXX. So now we can calculate all of these things. All right, so let's do some inference, all right? We are going to do a hypothesis test. We're going to say, okay, well, our null hypothesis, right, is that our beta, remember our hypotheses are in terms of the true values. So we're going to say beta 1 equals 0, right? There's no effect of makeup spending on demons killed. And our alternative hypothesis is we're just going to do a two-tailed test and say beta 1 is not 0. All right, we'll use a significance level of 0.05. And let's calculate this. So that would mean that we would have beta hat 1 minus, so our observed value minus our, hypothesized value, and it's going to be over the variance of beta hat 1. But what is the variance of beta hat 1? Well, let's say that for this we got 7, for this we got 1/16, right? So 7 and 1/16, I like that. So it would be the standard error would be the root of 7 over 1/16. That's about 0.5, right? And our observed beta hat 1 was 0.8. So that's going to be 0.8 over 0.25. And so that means that our t-stat, and so this is a t-stat. So this is going to be t distributed with n minus k plus 1 degrees of freedom. I should mention that k is the number of regressors in your regression, and we only have one regressor, only one x right now, so that k is going to be 1, and it's going to end up being n minus 2. Okay, n is the number of observations you have. All right, so that's t distributed. And as n goes to infinity, we can invoke the central limit theorem and say, yeah, that's approximately normally distributed, and we can use the standard normal distribution for that. Okay, so assuming that standard normal distribution right there, 0.8 over 0.25, is going to give us, what is that, 3.2? Yeah, something like that, something like 3.2. Okay, perfect. So if we get 3.2, that is more than 1.96, which is the critical value for a two-tailed hypothesis test and the normal distribution. So we find significance, right? Boom, 3.2, more than 1.96. That beta hat 1 is definitely significant. Furthermore, we could construct a confidence interval for this, and our confidence interval would look like our observed beta hat 1 plus or minus 1.96 standard errors, okay? And the standard error of beta hat 1 we said was 0.25, right? So that's about, 0.8 plus or minus 2 times 0.25. And so our confidence interval would be about 0.3 to 1.3. Again, we see that 0 is not in that interval, and so that is significant, right? And a way to describe our confidence intervals, this is a 95% confidence interval. So we're going to say, hey, if we ran this test 100 times, 95 of those times, 95% of the time, when we construct all these intervals, 95% of the time, the interval we construct is going to bracket the true beta 1, okay? And then 5% of the time, we'll make a bad interval, and it won't bracket beta 1, okay? But because of that, this is pretty, we feel pretty good about this interval that we've constructed. Okay, so that's it, right? Are we done? Well, oh, I forgot the r squared, right? Let me go over the r squared of this, I guess. So let me define these terms really quick. So you have, I'm going to say SST. What is SST? SST is the total sum of our squares. Okay, we're going to define that as the sum of all of our y's, the actual y's, minus, their deviations from the mean. Okay, so this is that total variance, essentially, of our model. Then we have the explained sum of squares. Remember going over the explained part is explained by a line. So that's going to be our predicted values, deviations from the mean. Okay, and then we have our sum of squared residuals. This is the variation that's left over. This is going to be literally just the sum of our squared residuals. Or we could also write that again as our y minus y hat squared. Y minus y hat. Yeah, that's a residual. Yep, I agree with that. So we have a total sum of squares, explained sum of squares, sum of squared residuals, and those are measures of our variation. So we know that this relationship is true, that the total sum of squares equals, that's going to be our explained variation plus our residual variation. If we were to divide all of this by SST, we would get 1 equals the proportion of our variation that's explained plus the proportion that is residual, right? Or in other words, our explained variation, or the proportion of our explained variation, is going to be 1 minus the proportion of our residual variation. Hopefully I said all of that right. Okay, so we could actually calculate our r squared. This right here, we call that r squared. All right, that is how well your model explains the variation in your data. Okay, so if we knew that, for example, SSR was 196, and if we knew that SST was, I don't know, 270, something like that, then we could calculate this. We would just put 1 minus 196 over 270 right here, and that would give us an r squared of, I don't know, about like 2.274 or something. Not like a super good fit. So, I mean, there's probably a lot more variation in your data. It's probably out here a little bit. But that would be, your r squared. Okay, so now we've ran a whole regression, and we've got significance, and we have our r squared, and we've answered our question, right? Like, yeah, looks like makeup spending does, in fact, affect how many demons you kill from this cross-sectional data set. We see that. Or does it? Okay, let's think about this. What are the assumptions that we're making that are underneath this model? Okay, maybe that's a valuable thing to go over. So let's talk about these assumptions. Okay, I'm going to erase some of this so we can dive a little bit into these assumptions. I'm going to erase a lot of this. Okay. All right, so let's talk about the Gauss-Markov assumptions. Gauss-Markov. Okay, what are the Gauss-Markov assumptions? The Gauss-Markov assumptions assume that we have a linear, full rank, random sample with a zero conditional mean and homoscedasticity. Okay, those are all things that we assume in the Gauss-Markov assumptions. And, we could, some do, break this down into kind of a different set of assumptions, A0 through A3. So A0, mathematically, would be that the existence of X transpose X inverse. Now, what is X transpose X? We'll get a little more into this when we talk about the matrix form of our regression, but essentially, this is your matrix of X's, okay? And X transpose X inverse has to exist. This means this is the same thing as being full rank, okay? So if X is not full rank, X transpose X, if X transpose X is not full rank, am I saying that right? Then when you try to take the inverse, you will not be able to. The math will literally break down. Your matrices will break because, when you try to take, I don't want to go too much into matrix algebra, but basically when you try to take the inverse, it involves 1 over your determinant. And if you have something called perfect collinearity, then this breaks. Okay, what is perfect collinearity? It's literally, I have X makeup spending. Let's say I add another regressor, X2, and X2 is going to be 2 times makeup spending. For some reason, I add that in. Well, this is a perfect linear relationship. Look at that. I have a regressor, makeup spending, and I have another regressor that literally can be calculated by multiplying 2 times makeup spending. It's a perfect linear relationship. If I put that in my regression, then that's perfectly collinear. And when I try to calculate my inverse, my determinant is going to end up being 0, and I'll get 1 over 0, and I can't divide by 0, so it breaks, okay? It just breaks. That's about as far into the matrix algebra as I'll go with that one. But you can't do stuff like that, okay? You can involve a nonlinear relationship. So I could say x1 squared. That would actually work because it's a nonlinear relationship. But any linear relationship, no, I can't put that in, okay? So x transpose x inverse, it's got to exist, okay? In other words, no perfect collinearity. All right. That's what full rank means. All right, so divide this into another assumption as well, which is our zero conditional mean, right? Our zero conditional mean is that, we all rewrote this, our expected epsilon given x. Basically, expected epsilon, our epsilon doesn't depend on x, okay? So we'll just set that as 0 because we can, it doesn't depend on x, and we can easily set expected epsilon to 0. So this is the zero conditional mean assumption. We also call this exogeneity, right? X is our exogenous. That has to be the case. If this is not the case, then OLS is biased, okay? It's biased, not good. We don't want OLS to be biased. So we got to assume that. Okay, we break it into another assumption. A lot of times, what's A2? We assume homoscedasticity. That's what we assume. So homoscedasticity is where we're saying, okay, the variance of epsilon given x is, again, just going to be the variance of epsilon, right? It doesn't depend on x. And we'll just call that sigma squared. All right, pretty simple. Okay, homoscedasticity, if I were to draw this graph, again, right, we don't want any of that going on. That was a terrible picture, but basically, like, we don't want the variation in our error terms to depend systematically on where we are with x. Okay, we want that to be the same level of variation the whole way through. So we assume homoscedasticity with the Gauss-Markov assumptions. And then finally, we also assume no serial correlation. No serial correlation is that the covariance of one error and another error given x equals 0. Okay, for, like, obviously the I and j, this is, when I is not equal to j, because then it would be the same error term. Okay, so the covariance of 2 errors is 0. They don't vary together. No serial correlation really comes up more in time series data. That's really what that refers to. But here, when we're talking about cross-sectional data, you can just think about this mathematical assumption is referring to that we have a random sample. Okay, our sample is random, so that the errors do not correlate with each other. Okay, and obviously it's linear. We defined a linear model here, so that's just part of how we set everything up. Okay, so under these Gauss-Markov assumptions, if these are all true, then OLS is blue. What does that mean? It is the best linear unbiased estimator. All right, well, clearly it's, an estimator. We get beta hat 1 and beta hat not, right? These are our estimators, and they are unbiased under this assumption right here. This assumption right here, all right, is what makes them unbiased. Any violations of exogeneity will bias OLS. Okay, it's a linear estimator. We already talked about that. What does best mean? Of all the linear unbiased estimators, the best one, that means it's the lowest variance. Okay, our standard errors will be the most precise if we use OLS under the Gauss-Markov assumptions. But if these assumptions break, then we don't have that anymore. Okay, if we have a violation of homoscedasticity, then our standard errors are off. Okay, they're wrong. They're just wrong. Okay, it could be too high, they could be too low. The fact of the matter is they're wrong. So you can maybe solve that by using, robust standard errors. I could fix that, right? If, again, if no serial correlation is broken, and we'll talk more about that in time series, but if that's broken, then again, your standard errors are wrong, okay? It doesn't, like neither of these bias OLS, this bias is OLS. But in that case, you could use Nui West, hack robust standard errors for that. All right, but that is the Gauss-Markov assumptions. And the one that I really want to focus on is this one right here, okay? This assumption that our error term is not correlated with our X. Or in other words, in this example, that the other factors that affect number of demons killed are not also correlated with makeup spending. Obviously, all of these things affect Y, but we don't want them to be correlated with X and Y. That is a problem. That's what we call an omitted variable. You would have omitted variables bias in that situation. Now let's think about that. Do we actually have that? Well, our zero conditional mean assumption is most likely to be violated when people can self-select, right? They can self-select into the amount that they spend on makeup. Is that true in our case? Well, obviously. Yeah, obviously people can choose how much they spend on makeup. That's a ridiculous question. So we probably have some omitted variables bias, because let's think, is there anything that could be correlated with how much you spend on makeup and how many demons you kill? I have one. How about budget, right? How about the budget of management? We have all these demon hunters from all around the world, and they're killing these different demons in these different places, but the budget of their management probably determines A, how much they spend on makeup, and B, how many demons they kill, right? They probably have better training, maybe in their more urban areas, and there's just a lot more going on, and so they're doing more performances, so they spend more on makeup, and they kill more demons. That, my friends, is an omitted variable, and exogeneity is broken, and OLS is biased. We have omitted variables bias. Okay, so let's chill. It's okay. Maybe we can just include it. We'll just include that in our regression. Hey, let's take the omitted variable out of epsilon, put it right in there. Boom. Problem solved, right? Let's control for that. Okay, so we'll need a little space for that, but let's do that. That sounds good. Whew. All right, that was a close one. Thought we were cooked. All right, so now we're going to estimate our model a bit differently, okay? Let's say that we'll have, let's call this x1i now, and let's have another beta. And let's say this is x2i, okay? And x2 is the budget of the management, right? It's it's your management budget, okay? That'll be good. So just as long as epsilon doesn't include anything else that's correlated with both x1 and y or x2 and y. Okay, there could be a few more things. Okay, well, maybe we'll find all of them and we'll control for all of them. Okay, so you'll have, a bunch of those all the way to beta k, x, k, I, and remember to still include our error term. Okay, now I'm assuming the conditional independence assumption, okay, the CIA. Obviously, CIA stands for something else, right? Culinary Institute of America, but we're not talking about that CIA. We're talking about the conditional independence assumption, meaning I am assuming that I can observe and control for all the things that are correlated with X and Y, and I can put them in here, and now exogeneity finally works, right? Now my expected epsilon, given my vector of x's, is indeed 0. Okay, so I'm making that assumption. This is kind of long to write, so I'm actually going to write this in matrix form, if you don't mind. Okay, so I'll write this model, and it'll be y equals x beta plus epsilon. See how tight that looks? That's it's very good, very good. Okay, so y is a vector of y's. Okay, it's going to be y1, y2, all the way to yn. Okay, all right, that's what y is. X is going to be a matrix. So x is this big matrix, and I'm going to have, for each individual, I'm going to have x1 for person 1, and I'm going to have, x2 for person 1, and, all the way down to x, this is x1, my bad. So this x1 for person 1, x1 for person 2, all the way to x1 for person n, okay, because I have n observations in my data set. Okay, then I'm going to have x2 for person 1, and x2 for person 2, all the way to x2 for person n. Okay, and these are going to go all the way down here So until I have, how many regressors? I have k of them, right? So xk for person 1, x k for person 2, all the way down to xk for person n. All right, so that is what my X matrix is. My beta, it's just going to be a matrix of betas. Beta naught, beta 1, all the way down to beta k. And then my epsilon is going to be a matrix of epsilons. We're going to have epsilon for person 1, epsilon for person 2, all the way down to epsilon for person n. Okay, let's make sure these matrices all line up. And we're not doing anything illegal here. So this is going to be an n by 1. Okay, so why is n by 1? So this should be n by 1 as well, right? Well, x is, let's see, an n by k. Am I doing that right? N by k? No. No, because we have, oh man, you know what? We need a bunch of 1s here. Yeah, we need a whole row of 1s just sitting there. Because remember, when we multiply this by beta, then we're gonna take each row, we're gonna flip it up, and we want something to be multiplied by beta naught, right? Beta naught sitting there. So we want a row of 1s right there, or a column of 1s. Okay, so there we go. Now it's an n by k plus 1. Exactly. Now our beta vector, that's going to be k plus 1 by 1. And so, and our epsilon is n by 1. Okay, so y is n by 1. Then we're adding something n by 1. And let's see what x beta is. X beta, n by k plus 1 times k plus 1 by 1 is going to give us an n by 1. Ah, so everything's n by 1. Perfect. Okay, so we're not doing anything illegal by our matrix form right there. Okay, perfect. That's how everything's set up. Now, let's see. What else is going to change in our multiple regression? Maybe I should say, instead of we're choosing the arguments that minimize our sum of squared residuals, right? But now, our sum of squared residuals, we're going to, let me erase all these right here. So our sum of squared residuals is going to be a vector of residuals. We're going to call that u hat. U hat is going to be our vector of residuals. So, we square it in matrix land by doing something like that, right? U hat transpose U hat. That's how you square something in matrix form. But keep in mind that U hat is going to be y minus x beta hat, right? Right? Actual value minus predicted value is, right? Because our predicted value, y hat, is going to be x beta hat. Agreed? Yeah, I'd agree with that. So actual minus predicted value, transpose actual minus predicted value, okay? So that is going to be, and we're going to choose the argument b, and b is going to be a vector, all right? Argument that minimizes that. Okay, perfect. And then we will end up, again, with our OLS beta hat, okay? And beta hat is going to be x transpose x inverse x transpose y. That is the formula now for beta hat. Okay, perfect. So that's our multiple regression OLS. And backing up just a little bit, why might we want to do multiple regression? Why did we even bother with this? Well, there's a few reasons, right? Why? Okay, we want to eliminate omitted variables bias. Okay, that is the biggest thing, right? That's why we started this, because we thought there were omitted variables. So we decided, let's just control for those variables. That's a big thing. But there are also, other reasons. Maybe you just care. You care about other x's. Okay, other regressors. So you want to add them in there, and you want to see the effects, the beta effects on them. You might want to allow for nonlinear functional forms. Okay, it's like when we talked about makeup spending and square of makeup spending. That would be a little weird, but maybe you think that makeup spending has a nonlinear effect on y, so you want to estimate that. Okay, so that would be another reason. And then also, the more regressors that you add, it's going to improve the precision of your estimates. Okay, you're going to have a better R squared, and your estimates will be more precise. So those are all reasons to run multiple regression, and that's why we're doing this whole thing in the first place. Okay, but let's get back to it. So we defined beta hat, we defined y hat. and our matrix forms and everything, how does this change our inference, right? We're still estimating our cross-sectional data by OLS, but how does it change our inference? Whew, this was already like, kind of confusing to begin with. Well, thankfully, the variance of epsilon is still going to be SSR over n minus k plus 1, okay? We're done with that. Okay, that's good. And then what's the bottom of this going to be? Well, instead of SXX, it's going to be a little bit different. It's going to look like this. So it's going to look like SST of our, so sorry, this isn't the variance of beta hat 1 anymore. This is going to be the variance of any beta hat. Call it beta hat j. Okay, so the variance of some beta hat j is going to be the SST of xj times 1 minus r squared j. And what this means, this is the total sum of squares from regressing xj on all your other regressors. You have a bunch of regressors in your equation now. So this is going to be total sum of squares xj regressing in all your other regressors. And that's where the r squared comes from as well. All right. So r squared is going to be, if they're highly collinear, x and your other regressors, if they're highly collinear, your r squared from regressing on your other regressors is going to be very high. And so this denominator is going to be 1 minus almost 1. You're going to get close to 0 there, and your variance is going to blow up. Okay, not good. But you can examine how in the bivariate case, where you just have one regressor, then what's your r squared from regressing on all your other regressors? Well, you don't have any other regressors, so your r squared is 0. So this is going to be 1 minus 0, and this just is your SST, for xj. It just goes back to the SXX that we had before. Okay, so it's the same formula. It's just a little bit, more specific now, more general. Okay, all right, and then something else that you can do when you have multiple regressors is an F-test. Okay, so an F-test is really when you're testing multiple hypotheses. Okay, I'm going to write down the formula for our F-stat right here, and then we'll talk about it. But it's SSR restricted minus SSR unrestricted over Q over variance of sample variance of epsilon. Okay, sigma hat E squared, which we already defined over here. You know the formula for that one. It's by the I. I don't know what's by the I. It's just let it be. Let it be. Okay. So this is our F-stat. So an F-test, again, is for testing multiple hypotheses. What's multiple hypotheses? Well, how about beta naught? I don't like beta naught. Beta 1 equals beta 2 equals 0. And that's a multiple hypothesis, right? We're testing beta 1 equals 0 and beta 2 equals 0. We have two hypotheses in here because we have two equal signs. Okay. So that's our number of restrictions. Okay. When we're running an F-test, we are restricting our regressors, we're restricting our coefficients to 0. So I restrict beta 1 to 0, restrict beta 2 to 0, and run my F-test. So my sum of squared residuals restricted is the fit, or it's actually the residual variation from my regression where I assume beta 1 and beta 2 are 0. I restrict them both to 0. Okay, and I subtract the SSR unrestricted. That's from my regular regression with everything included. Okay, so all right, does that make sense? So basically, SSR minus SSR restricted minus SSR unrestricted is measuring how much worse the fit is when I restrict these to 0. Okay, and we're going to measure that per restriction. Q is the number of restrictions here. It's going to be 2 in this case, right? 2 restrictions. So basically, what an F-test is saying, what an F-stat is saying, is it's saying how much worse is the fit in my restricted model per restriction relative to the variation in my data. Okay. If it's a lot worse, you get a high F-stat, and that means that these are actually jointly significant. If it's really not worse and you get a very low F-stat, then they're jointly insignificant. Okay, and that is how an F-test works. Okay. Talked about a lot of stuff. Do I want to say anything more about any of that? No? Okay, let's move on. Enough with this cross-sectional, okay, let's actually we'll stay in cross-sectional land, because even though we did all of that, we did our multiple regression to solve all of those problems, or to solve, omitted variable bias, really, do we still really believe the conditional, or I erased the CIA, the conditional independence assumption? Do we believe that we really control for everything that affects both X and Y? That's kind of a strong assumption, okay? And that's not the only thing that can go wrong with OLS either. The thing is that OLS has so many problems with it. OLS problems, right? And just like OLS, when it has problems, it irks me. It's like saying it irks me, but like it orks me. Anyway, like OLS, it can have omitted variable bias, right? We already talked about that. That's a huge problem. Exogeneity problem right there. Reverse causality and simultaneity. Those are pretty similar concepts. Reverse causality says, hey, not only does Y depend on X, maybe X depends on Y. Maybe the amount that a demon hunter spends on makeup is in fact dependent on how many demons they kill. Maybe when you kill demons, you become more confident and you go out and you spend more on makeup, and you just kind of splurge. Or what if you get commissions? What if you get commissions from killing demons, huh? Or bounties, right? Then you'd have more money. That would definitely spend, or definitely affect how much you spend on makeup. I need a drink. Yes, it would. Okay. So reverse causality would also violate exogeneity and simultaneity too. Okay, simultaneity is when two things are determined at the same time, like supply demand. They're two peas in the same econometric pod. So that's not good. All right. Or you could have measurement error. What's measurement error? People reporting how much they spend on makeup, they're wrong. Okay, they just guess. They say, I think I spend about this much on makeup. So really, you're not even evaluating how much they spend on makeup. You're evaluating a blurry version of this. Okay, so when that happens, you get attenuation bias, which just means that your estimates are going to be biased towards zero. All right, so they're going to be weaker than the actual relationships. These are all problems. But what if I told you we could solve all of these problems with just one magic method? Oh, now you're interested. Okay, this is called instrumental variables, my friends. That's right, IVs, instrumental variables. Basically, we are going to get a secret agent variable to help us, someone to dive into that regression and analyze the actual effect for us by just like moving through all of those different problems that OLS has. Okay, how does an IV work? Well, an instrumental variable is a variable we use to instrument for X. It's like a placeholder for X that helps us find the true effect on Y. But a couple assumptions still need to hold for IVs to be valid, okay? So the first assumption is we're going to mathematically state that. Okay, let's state these in terms of covariance. So we're going to call our instrument Z, okay? So first assumption that needs to hold is the covariance between Z and epsilon does need to be zero, okay? So we haven't gotten completely away from exogeneity, okay? Because we still need that to hold. But the covariance between Z and X, that needs to be non-zero. Okay, we definitely need it to be relevant. So we need exogeneity and exclusion. We'll talk about how that means both of those things. And we need relevance, okay? We need it to be relevant, we need it to be exogenous and exclusive. Exclusion means, exogeneity means that Z is not correlated with anything else that affects Y. Exclusion means that Z only affects Y through X, okay? It indirectly affects Y through X. If I were to draw this in a little graphic graph form, little picture, I might draw it like this. I might say, okay, here's your Y, here's your X, here's your Z. There's, also epsilon, right? So epsilon and X both affect Y. We assume that in our model, okay? Now Z affects X. That is the relevance assumption, or Z covaries with X. Okay, that's relevance. Exogeneity means that Z and epsilon are not correlated. Okay, Z and epsilon, not correlated. There's other things that affect Y. Z has nothing to do with those things, nothing at all. But we also, so that's exogeneity. And then we also assume exclusion. Okay, exclusion means Z does not directly affect Y. It only affects Y through X. Let's find an instrument. Okay, we've talked about this in abstract terms. What would be an instrument for makeup spending? Instrument for makeup spending. It's got to be related to makeup spending, but it needs to be zero covariance with epsilon. How about this? How about our instrument is a makeup promo, or makeup promos in general. Okay, hear me out. So, instrument, makeup promos. You can measure that as, for example, how many celebrities promoted makeup products that month, or a certain brand of makeup products, or whatever. Okay, something along those lines. Now, is celebrities promoting makeup, is that associated with demon hunters spending money on makeup? Yeah, I would say that's probably relevant, right? The more celebrities promote makeup, the more makeup spending there is in a given month. Yeah, that checks out. Okay, now exclusion. Does it only affect demons killed through makeup spending? Let's see, celebrities promoting makeup. I don't see why that would affect X not through makeup spending, right? Or affect Y not through makeup spending. Yeah, I don't see any reason why celebrities promoting makeup would affect demons killed. So I think we're good on that. Now let's look at exogeneity. Is celebrities promoting makeup truly uncorrelated with other factors that affect demons killed? This one is always a little bit tougher. I think it's relatively plausible, but you could definitely think of cases where it's not plausible. For example, let's say maybe there are certain times of the year where it's busier, or maybe not certain times of the year because we're just in this given month. But let's say just different areas in general. Maybe in more urban areas, celebrities promote makeup more, and there's more demons killed. So epsilon would be urban areas, and you'd get celebrities promoting makeup, and you get higher demons killed. That might be a violation of exogeneity, don't you think? You could maybe try to say, well, maybe just like celebrity influencers online. I don't know. See, it's really hard to find a good instrument. Okay, if you find a good instrument that really holds for these things, then you're set. Okay, because you can solve these problems with OLS. But let's just say, that's our instrument. It's not, the greatest instrument, but we'll take it. Okay, mostly because I can't actually think of anything else. So how is our IV calculated? You might say, how do we estimate that? All right, well, first of all, we're not in OLS land anymore, we're in IV land. All right, and let's get rid of this inference and write down how you estimate this IV. It's actually pretty darn close to OLS. IV is going to be the covariance of Z and Y over the covariance of Z and X. All right, that's pretty cool. Now that's in the bivariate case. Okay, if you have a matrix version of your IV, then your beta hat vector for your IV is going to be Z transpose X inverse Z transpose Y. And I should mention this is where if you have multiple IVs, this is where I'm going to write IV down here actually, where you are just identified. What does that mean? Well, you could actually have multiple instruments. Okay, why not? It's really hard to think of one, but if you're really good, you can think of several. And if you have multiple instruments, then you can use multiple of those instruments for one regressor. There are some reasons that you might want to do that. We'll talk about that in a second. But if you have exactly as many instruments as you have endogenous regressors, then you're just identified. If you have more instruments than you do endogenous regressors, then you're over-identified. It's okay to have more, not okay to have less. Can't do under-identified. We don't do that. Okay, you need at least as many instruments that you have endogenous regressors. Okay, so this in matrix land, this is your just identified version of IV. But we don't want to just do that. Okay, we want more. We want more IVs. Okay, so why would we want more? Tell me why. Ain't nothing but a heartache. Okay, so if we, why? I think did I have why there? No, I had it there before. So why would we have more instruments than we need? Well, here's a reason, right? This would be obvious. If you have more than one endogenous X, okay, well, all right, that's not more instruments than you need. That's just, why would you have more instruments? Okay, it's kind of a dumb reason, actually. I'm going to erase that one. Okay, what's another reason? Okay, precision. Having more IVs increases precision of your estimates. We kind of already discussed that before. But really, it also allows you to test if your IVs are valid, right? That is your covariance of epsilon and z equals 0. You can test that. You can test for your exogeneity exclusion assumption. Now, if you are over-identified and you have more instruments than you need, then you can't just use these IV estimation methods. You actually need to use 2SLS to estimate that, right? Two-stage least squares. How does two-stage least squares work? Well, I'll explain it to you, okay? It's actually very simple. Two-stage least squares. Where are we? Okay, so first, in two-stage least squares, you regress your x's on your z's. All right, regress x on z, and you end up with the residual from that, right? Regress x on z, and you end up with, sorry, not the residual. Sorry, this is your predicted value. You're going to regress x on z, and you're going to get your predicted value from that regression. Okay, then you're going to regress your y on your predicted value from that regression. Okay, and when you do that, that will give you your estimate beta hat for your IV. There you go. So this is the first stage. This is the second stage. That's why they call it two-stage least squares. Okay, and that's how you estimate IV if you are over-identified. You can do it if you're under-identified, and it'll just collapse to the sorry, not under-identified. You can do it if you're just identified, and it'll collapse to your normal just identified case. But if you are over-identified, you have to use two-stage least squares. Okay, it's not an option anymore. You got to do it. Okay, so let's go back. We said that we could test these assumptions, that our IVs are valid. What are some tests that we might be able to do for those? Well, I'll show you. Okay, it's really easy to test relevance, covariance of z and x. I mean, you just plug in the covariance of z and x, find out what it is. But exogeneity exclusion, a little bit trickier. But there are ways, they're not foolproof. They won't give you an exact answer, but they will tell you if you're really wrong. Okay, so they will catch some bad errors that you might make. So the first one is the Hausman test. Okay, how do you do a Hausman test? And Hausman test? First, you're going to IV regress. I mean, you're going to do your IV regression, right? Your x on all of your z's, right? Okay, so you're going to use all of your z's as an instrument for x in an IV regression. You're also going to run an IV regression where you regress your x on a trusted subset of your z's. This is really important. These are the instruments that you know are valid. You're like, I'm sure that these instruments are solid. That's very important for this test to work, okay? So then you're going to have a null hypothesis that the beta hat from all of them minus the beta hat from your subset is 0. Like they don't, there's not any problems with consistency. They don't converge to meaningfully different things. Whereas your alternative hypothesis is that is not 0. Okay, they are meaningfully different. And if they're meaningfully different, that means that there is a problem with at least one of your instruments. Okay, at least one of your instruments is invalid if you reject the null hypothesis. Okay, so that's how a Hausman test would work. And you would have your beta hat all minus beta hat subset, right? So this is what you're testing minus the hypothesized value of 0 over the variance of beta hat all minus beta hat subset. But what is that variance, you might say? How do I get that? Well, this is why it's called a Hausman test, because Hausman was the guy that found out that this variance actually, this should be a standard error. Sorry, it's the square root of that variance. So this is the standard error, okay? So that variance is actually just the variance of beta hat all minus the variance of beta hat sub. All right, isn't that crazy? Isn't that crazy? It's just the difference of the variances between those two. So that's how you run a Hausman test, okay? That's one test you can run. You can also run an omnibus test, that's a very loose general term. I won't call it this. This is this is called by different names. You could call it an omnibus overidentification test, or also more specifically a Sargon-Hansen J test. Okay, that's what we're going to call this test that we're doing right here. How do you run this test? Well, first of all, you're going to do 2SLS. You're going to do two-stage least squares, and you're going to use all of your z's to do 2SLS there. Okay, and then you are going to get your residuals from this. You're going to get your residuals u hat, which is your y minus x beta hat. Okay, then you are going to regress your residuals on your z's. Okay, that's what you're going to do, and then you're going to take the r squared from that regression, and n r squared is going to be, wait for it, it's going to be chi-squared distributed with q minus r degrees of freedom, okay? R is the number of endogenous regressors that you have, and Q is the number of instruments. So basically, this degrees of freedom, this is just your level of over-identification. So maybe you have one regressor you're testing, one endogenous regressor you're testing, and you have 3 instruments, right? So your level of over-identification is 2. You have 2 degrees of freedom in your chi-squared test. The Hausman test and Sargon-Hansen test, like the outcome is going to be the same when you accept or when you reject or fail to reject. If you reject these tests, then at least one of your instruments is not valid. Okay, there's a problem. If you fail to reject, then your instruments might be valid. Okay, it doesn't mean they are, they just might be. All right, it just didn't catch that they were invalid. So that's how those IV tests work. That is IV testing. So, okay, maybe Zoe decides, all right, I was thinking about the IV thing, it would fix the problems with OLS, but you know what? I want to just get rid of all of that. And who needs cross-sectional data? Cross-sectional data is boring. All right? So here's what we're going to do now. Make sure we're still recording. It'd be very unfortunate. Here's what we're going to do now. Instead of cross-sectional data, I am going to go, I don't think we need these here anymore. I am going to go with time series data. Time series, okay? What is time series? Well, it's for my model. Looks more like this. I have a y, t, okay? So Zoe's just going to use herself now. She's going to use her history. She's got a long journal. She takes really good notes, okay? She's going to say, okay, the number of demons I kill in a certain month is going to be some linear combination, right? There's a beta knot. Some linear combination of the amount I spend on makeup in a given month, and then plus some error term. Actually, in time series land, we often call that U, okay, UT. So that is her new model. She's using time series data now, which is just Zoe over several months. All right, time series data. Let's go back to OLS to estimate that. All right, so time series data is cool. It's really cool. One of the things that you might do is say, okay, this is still kind of a static model, kind of a little boring. It's just saying that the amount of demons I kill this month is related to the amount I spend on makeup this month. But what if I want to spice it up a little bit? What if I want to say, okay, it's not just about the amount of I spend on makeup this month. I'm going to start using deltas now. Delta not, or do I want to use a delta not for that? Yeah, let's do that, xt. So it's dependent on the amount I spend on makeup this month, but what if, maybe she stocks up on makeup. Maybe she spent a lot on makeup last month, and the makeup she spent that month, that last month, is helping her kill demons this month, right? So then she could add another effect. She could say it's also related to how much I spent on makeup last month, and it even might be related to how much I spent on makeup the month before that. Okay, it might affect the number of demons I kill for several months. How many months? I don't know. Let's say Q. Oh, that's a 2. Let's say Q months, right? So delta Q, X, T minus Q. And don't forget our error term. Okay, so this right here is what's called a finite distributed lag model. This is a dynamic model now. Okay, dynamic, meaning we're doing multiple time periods in the past. Okay, we're getting crazy with it. Okay, so there's a finite number of lags, all right? And that's why it's called finite distributed lag model. We're finitely distributing the lags, okay? So that's one way she can estimate that. She also realizes, though, that in time series OLS, there's some problems, okay? We didn't get away from the problems with time series. In fact, we might actually end up creating more problems with this time series thing, okay? So let's look at those Gauss-Markov assumptions again, and let's look at them really closely. So we already know the existence of an inverse. I'm going to go with the A0 through A3. A1, okay, exogeneity, right? We assumed, and now in time series land, that the expected epsilon t given, and let's assume that this is let's make this not dynamic. I'm just going to go back to a flat model to describe to you the fact that these things happen even when you're not using a finite distributed lag. Okay, so there's your UT, and maybe you have more betas there and everything. But your expected epsilon t given your vector of x's, right, is equal to 0. Okay, epsilon is not related to your x, your makeup spending from any time period. This is what we call strict exogeneity. Okay, very strict. This is what we need for OLS to be unbiased. Again, all right. There's also like a looser form. This is called contemporaneous exogeneity, which means that our expected epsilon t given xt equals 0. So contemporaneous meaning in the same time period. Our error term from that time period is not correlated with our x in that time period. So contemporaneous exogeneity says, hey, maybe our makeup spending from last month, maybe that is related to how many demons we kill this month. But our makeup spending this month, that's not related to other, sorry, I said that a little incorrect. Maybe our makeup spending last month is correlated with other factors in epsilon, right? Other things that affect makeup spending, or epsilon last month is correlated. Factors that affect demons killed is correlated with makeup spending in a different time period, like last month. Okay, geez. But for this month, they're uncorrelated. In this case, probably not the greatest assumption, even with contemporaneous exogeneity, because really, like this month, makeup spending is probably correlated with unobserved factors. I mean, we already talked about omitted variables that could be present there. And we'll talk about a couple more, actually, that pop up now that we have time series data. But strict exogeneity would say, no, your epsilon is not correlated with x from any time period. So makeup spending last month cannot be correlated with the error for this month and vice versa, right? Those shocks need to be completely independent with each other, which is a really strong assumption. Okay, even contemporaneous in our case is kind of a strong assumption. But under contemporaneous, remember, OLS is biased. You need this for OLS to be unbiased. So with contemporaneous exogeneity is biased. It's still consistent, though. But that is a looser assumption. Okay, so that's A1. And then let's talk about A3 as well. A3 was when we talked about no serial correlation. And this is when it's really becoming important. No serial correlation becomes important in time series data. Remember, that's saying that the covariance of epsilon I and epsilon j given x is 0, when I is not equal to j. Sure. Yeah, that's no serial correlation. So that's saying that our error terms are not related to each other across time periods. So, hey, a shock that affected demons killed last month, that doesn't affect demons killed this month. Interesting assumption, given that, maybe so we got really sick or out of our game, and this is a several month thing. That means that your error from last month is going to be correlated with your error from this month. So that covariance is not going to be 0. So that shows up, that pops up in time series data. Got to watch out for that bad boy. All right. So those are some things that will pop up. There's some pitfalls to time series data. Pitfalls, it's going to keep going. Let's talk about how omitted variable bias expands here. You can have trends, or you can have seasonality, okay? Seasonality. What are those? Let's say we graph the makeup spending over time, okay? We graph our makeup spending and our Y. Sorry, I guess this is time. So let's say we graph these things and we find out that, over time, our demons killed is going up. Yeah. And let's say we graph our makeup spending and that's also going up. And so we see makeup spending and demons killed both going up together. And you know what this is going to cause if we run a regression on it? It's going to cause spurious correlation, okay? Which is just a fancy term for OVB in time series land. All right? It means that we see this trend. Why are these both going up over time? It's not because they're related to each other necessarily. It's just because time is passing, right? Like that's just life. Zoe is going on through her life, and she's killing more demons, and she's also spending more on makeup. That's just kind of what's happening as she's maturing as a K-pop star and as a demon hunter, right? So that's bad. Okay, that's going to give us spurious correlation. And so, I mean, we can also have, let's say it wasn't like a trend necessarily. Let's say you looked closely among certain months, and makeup spending did something like that. And let's say that actually demons killed also did something like that. Well, look at that. Like that is a clear seasonality right there. There's different periods where they both go up and down together. Does that mean they're related? Your regression will say it means they're related, but really what it means is just that there are certain seasons where you spend more on makeup and you kill more demons. These are like busy times. These are like critical times. Maybe at a couple different points in the year where you're having these big shows and a lot is going on. Black Friday. There's a lot of makeup spending because you're doing super big shows. A lot of people are out, and you're killing more demons. Demons are just out there. So seasonal times, right? You have seasonality. That's also going to give you spurious correlation. It's bad. OLS is biased. Okay. So what are you going to do? What are you going to do with trends of seasonality? Okay. You're just going to detrend. It's not that hard. It's not that hard, guys. All right. So you take your little regression, okay, and you just say, hey, I'm going to include time. And there we go. We're done. When you include time, include your omitted variable, and you're chilling. Or if it's seasonality, you're going to include like a dummy for every season. Like let's say you have it's truly a seasonal thing. It doesn't have to be literal seasons. It could be months of the year. Let's say it's months of the year, actually. So let's say you include a dummy variable, and a dummy variable just says, okay, this variable is going to equal 1 if it is January. And if it's not January, this variable isn't going to be in there. And you're going to do the same for February, and the same for March, and you have all these variables. Now, you need them for every season except one, okay? You cannot include a dummy variable for every single season. You know why? Because if that happens, you have perfect collinearity. We talked about that before. You can't do that, okay? If you have perfect collinearity, if you have 12 months of the year and you have 11 of your variables that say it's not this month, guess what? You can take those 11 variables, and if they're all 0, you know what the last variable is. That means it's a linear combination of the other 11 variables, and if you include all of them, you now have perfect collinearity, and your inverse does not exist, okay? You have fallen into the dummy variable trap. So don't do that, and instead of doing that, just include 11. And then your regression is going to be based off of your beta knot right here, right? That's going to be the it's going to be the dummy that you leave out. Okay, so all of the effects on your dummies that you include, it's going to be all of your coefficients. It's going to be the effect over the dummy that you leave out. So if you leave out January and include February through December, then the coefficient on February is going to say, okay, what is the difference between February and December for demons killed? That's how dummies work, okay? So detrend it, include time or include dummies. Or, another way you could do this, I guess, is with something called partial regression. This is the Frisch-Waugh theorem. And a partial regression just says, your you're going to regress your x on your t and get, residuals. Call it u hat. You're going to regress your, let's see, yeah. You're going to regress your y on your t. You're going to get residuals. We'll call that v hat. And then you're just going to regress those on each other, right? You're going to regress your u hat on your e hat. Is that how you do that? I think that's how you do that. Okay, so you regress your x on your t, your y on your t. Maybe that's flipped. Yeah, that's definitely flipped. Yeah, I was like, something sussy is going on there. So yeah, do that. Regress your y on your t, then regress your x on your t, then you regress the residuals on the residuals. And that is the Frisch-Waugh theorem. It's called partialing out or partial regression. And that's another way of you're going to get the same thing. Okay, you're going to detrend by doing that. Or you can just include t or dummies for your seasons. Okay, so that's how you deal with trends and seasonality, but that's not the only problem, guys. It's not the only thing that can happen. You know what else can happen? I'll tell you. Dependent data. What is dependent data? It's where some of your data follows a process that is dependent on other data. It's kind of vague, but here's two ways that can manifest. One is called an autoregressive process. An autoregressive process, let's say of order q, because it's of a certain order. An autoregressive process is where your, let's call your variable, it could be any variable. I'm going to call it x now. Your x in a certain time period is going to be dependent on, here's x from a previous time period. Okay, so it's dependent on itself, hence the name autoregressive. All right, and then maybe it's, there's row 1, maybe row 2 is, some other scale of effect from itself from another time period. And if it's of order q, this happens q times, right? So pq x t minus q. All right, plus, obviously the base, the shock from that specific time period t. Okay, so this autoregressive process, all right, that's not good, all right? Especially if your row equals 1. What does that mean? It means that in one time period, then you're going to get 1 times that in the next time period. And then you get the full thing in the next time period. See, if row is less than 1, then eventually that's going to die out. But if row is 1, it's never going to die, ever. Okay? So if it never dies, then you have what's called strong dependence. Otherwise, it's weak dependence. And, we can deal with that. But strong dependence, that's a little bit of a different problem, okay? Let me talk about another process really quick that can happen. This is a moving average. A moving average of order q is where your variable is going to be dependent on some errors from previous time periods. So let's say this is e t minus 1, and then, you get another row, e t minus 2, and it keeps going, and then, you of course have the same et as well. Okay, so now your error, instead of your variable itself persisting autoregressively, you have your errors persisting in your variable for multiple time periods. Okay, that's what a moving average is all about. And so a moving average will die out. That's weakly dependent. It just takes so many time periods for that to happen. But here's the deal. Okay, here's how you know how big of a problem this stuff is. If your error term, if that follows an autoregressive or moving average type dependent data, then you have a violation of no serial correlation, right? That is violated if your error term is dependent on past error terms in whatever manner, okay? So in that case, hey, you know what? Use Nui West, hack robust, standard errors, all right? And that will solve that problem, all right? You fixed your weak dependence by doing that. Perfect. Now, if your y or x follows an autoregressive or moving average, but it follows it weakly, as in row is less than 1, then that also, it's not as big of a problem, okay? But if your y or your x is strongly dependent Okay, it follows an autoregressive process, and your row is 1. That means you have a unit root. That's a problem. Okay, unit root meaning 1. The root row is 1. Whatever. Okay, the point is that it's strongly dependent, and you got to fix that. Okay, you got to fix that now. So the way you do that is you just take whatever variable it is. Let's say it's y. Okay, and you're just going to take yt minus 1. Okay, that's your delta yt. Okay, and now this is what you're going to use. Instead of your old variable, same thing if it's x, you take delta xt. Okay, whichever one is following your autoregressive unit root process. Okay, you're just going to do this difference of one time period, and you're done. Okay, because that will subtract its dependence off, and you'll be good. Okay, so that's how you deal with that. All right, so Zoe finds out, oh, wow, I thought time series was going to be super cool. It actually has all of these problems. So you know what? Forget that. We are not doing that. You know what we're doing now? We are moving on from time series to panel data. Make sure we're still good. We're rocking, boys and girls. Okay, so in panel data, what you have is sorry, panel data, what you have is basically like a 3-dimensional cross-section, okay? You have all of these different demon hunters. You have their spending on makeup. You have their demons killed. And then you have this for all these different individuals over multiple time periods. So we called OLS, pooled OLS in this case. BT dubs, the difference between a pooled cross-section and panel data is in a pooled cross-section, you're polling these cross-sections from different time periods. They're all different individuals though, okay? So you have some individuals over here, some individuals over here that might be from different time periods, but you're basically bunching those all into one data set. Whereas panel data is literally the same individuals, the same cross-section over time, 3-dimensionally, right? So that's the difference between those. And so, okay, so in this case, our model looks a little bit different. Let me write this out. So our model is going to look like YIT. Okay, we have the demons killed for an individual in a certain time period, and it's going to be some linear combination of the makeup spending for that individual in that time period. Okay, we have a bunch of demon hunters over several months. All right, that's how we're laying this out. And then it's going to be, plus you're going to have multiple regression and everything, but then you're going to have plus epsilon IT. And typically we actually break up epsilon here into a couple different pieces. We can say alpha I, and alpha I is the error that's related to an individual's characteristics. Okay, this is what makes an individual different from everybody else. All right, that's their alpha. And then you have some truly idiosyncratic piece. We'll call that nu IT. That's a nu there. And that is, truly random, right? Over individuals and time periods, it's a different, more random shock. All right, at least that's the model. That's what we're going with. So in this case, remember that we're still, if we're using OLS, we're still assuming exogeneity, which here, let me write it in terms of covariances. We're assuming that the covariance of nu IT and xit, right, is 0. And we're assuming that the covariance of alpha I and xit is also 0. Okay, so in this case, the random shocks between individuals and time periods, we assume, or I shouldn't call it random shocks because that's, implying an assumption. Basically, the other things that affect demons killed across individuals and time periods are uncorrelated with makeup spending in that individual and month. But we're also assuming that the covariant, the makeup spending for an individual in a certain month is unrelated to the characteristics, the unique characteristics of that individual. Now this like believable, right? This really, you're telling me that Zoe, that her makeup spending is not correlated with the unique characteristics that make her Zoe? I'm saying like in econometrics, this is something that we call sussy. Okay, that is sussy. We got a problem here. So I can believe this, okay? You want me to assume that exogeneity? Fine, perfect. But this, sorry, I'm not buying that, all right? So we got a problem of the sussy alpha. And so that is what pooled OLS is going to give us, is a sussy alpha. So how do we fix the problem of the sussy alpha? Okay, I got 2 ways for you, my friends. 2 ways. Let me give you these 2 ways. The first one is called first differencing. All right, and here's what we're going to do. This first differencing is where you murder alpha. Okay, how do you murder alpha? Well, it's actually pretty simple. Okay, you are basically going to take your delta YIT, regress it on, okay, let's see, your first differences is where you take YIT minus YIT minus 1, okay? It's a little different than what we just talked about with solving strong dependence, because not only are you just like changing one variable, you're changing your whole regression, okay? So your whole regression is going to be this whole thing minus this whole thing from the last time period, okay? So basically, your YIT minus 1, what's going to happen there? Well, your delta YIT, if you run this regression, is going to be your beta naught, the same in both time periods. Beta naught's going to get murdered. It's beta naught minus beta naught is 0. So then you have beta 1, and then you have a difference in time periods there. So this is going to be beta 1 delta XIT, okay? And then your epsilon IT is going to be differenced. And this is going to be different, but this is not. All right, alpha I doesn't change across time periods. So alpha I is going to get murdered. Okay, so then you're going to end up with your delta nu IT. And that is your first differences regression. All right, so you have solved the sussy alpha problem by murdering alpha I. Okay, maybe you're not that extreme. So instead, we have fixed effects for you. Fixed effects, much nicer. Okay, you're going to include alpha I. Let's just be inclusive about it, okay? So let's go with that. If we include alpha I, then our regression looks more like YIT. Okay, we're still going to include beta naught. We're still going to include our beta 1, X, X1, X2, all of those ITs, if you have a multiple regression. And then we'll include something else. We're going to include a set. I'm going to write this in set notation, or in brackets. We're going to include a set of dummies for alpha I. Now remember, for dummies, you always exclude 1, okay? But we're going to, it's going to be like alpha 1, alpha 2, alpha 3 times a dummy saying, are you Zoe? That's the dummy. Like equals 1 if you're Zoe, equals 0 if you're not Zoe. Are you Rumi? Equals 1 if you're Rumi, equals 0 if you're not Rumi, okay? So all of these are going to equal 0 except 1, for every individual. Okay, so then you have a set of dummies. I'm just going to write it like that because I don't want to write a bunch of dummies. But then you're going to have plus nu IT. Okay, so this is fixed effects. You're including your fixed effects for every single individual. Okay, now fixed effects is also the exact same. It gives you the exact same result as what's called the within transformation. What is a within transformation? Well, it just says, you have your, I'm going to call this Y squiggle. Your Y squiggle IT is going to be beta 1 X squiggle IT plus nu squiggle IT. And the squiggle is going to be just your deviation from the mean. Why am I blanking on this? So the mean YIT minus Y bar I. Is that squared? No, I think it's just like that, right? Yeah, let me make sure I put that right there. It's just going to be just a little bit of a break right here. Okay. Yes. The squiggle is YIT minus Y bar I. Okay, so for every individual, you're going to have the YIT, and it's going to be that observation minus the mean of that individual. So the mean of that individual is going to be their outcomes across every single time period. You're going to take the mean of those, subtract it from every one of these, and so this is the within transformation. And this actually, if you think about it, this also murders alpha. but it gives the same effect as fixed effects. What's interesting is that fixed effects, especially if you have a lot of dummies, it's really intensive for a computer to include all of those dummies. So when you run this in Stata, it'll actually do the within transformation. So it's actually not being inclusive, it's still murdering. So it looks inclusive on the outside, but it's still the mafia in the background. So take that for what it's worth, okay? So that's what's going on with the fixed effects within transformation. Those give you the same result, or first differences. Those are both ways of dealing with the Sussy alpha problem, okay? And both of them ultimately end up in murder. So there you go. All right, so there's a special case. All right, let's say we want to talk about this special case. And we're going to call this special case difference in differences. What is difference in differences? Only one of the greatest things. Okay, so we're going to have two groups. We'll call it a non-treatment group and a treatment group. And we'll have two time periods, before and after. Okay, this is our Y. This is our demons killed. All right, so let's say, all right, Zoe thinks, okay, let me just examine. Let me go back to, okay, yeah, I'll stick with the panel data. I mean, this is a very this is a 2-period panel data. So again, special case. But she's saying, okay, I'm going to look at Tokyo and I'm going to look at San Francisco. Let's call this non-treated group San Francisco. Let's call this Tokyo. And San Francisco and Tokyo have, data for number of demons killed. Okay, before and after. And San Francisco maybe looks like, that. So we'll draw a little line there. And Tokyo maybe looks like, looks more like that. Okay? And what happened in Tokyo? Why are we calling it a treatment group? We're calling it a treatment group because in Tokyo, there was a makeup extravaganza. Okay? So that's what happened in Tokyo. There was a huge makeup extravaganza. All these people came and they got a bunch of free makeup. All right? So this makeup extravaganza, we're going to see what is the effect on demons killed. Okay, we really want to know that. And we're going to use difference in differences. So difference in differences is estimated like so. Essentially, do I want to write this first or that first? I'll write this first. Okay, I'll write this first. So you're still using the same model, but let me write it slightly differently. You got your beta naught plus beta 1, and then I'm going to say treated. This is going to determine the individual. Okay, it's equals 1 if you're the treated group, it equals 0 if you're not. All right, beta 2 times after t. All right, so this equals 1 if you're after the time period and equals 0 if you're not. And then beta 3, and this is going to be treated times after. So this is an IT type thing. And this is going to equal 1 if you are the treated group and after the time period. All right, and then you're going to have some error, some new IT there as well. I'll erase those. Okay, so what's going to happen is we are going to assume that this is essential to difference in differences assumption. We're going to assume that the trend that occurred in San Francisco would have occurred in Tokyo had Tokyo not had a makeup extravaganza. All right, so we're assuming they're very similar groups. All right, and that is what would have happened without the makeup extravaganza. All right, so this is where this leaves us. Let me put all of these in. So this is your intercept. This is where you start. Non-treatment group. This is where we start. That's our intercept, beta naught. Then we have beta 1. This is the effect of being in the treated group. So the effect of being in Tokyo, you see Tokyo starts a little lower than San Francisco. So I'll actually call that negative beta 1 because beta 1 is going to be negative. Okay, they go a little lower to start off. Then beta 2 is the effect of being after the time period. We can see that from San Francisco. This is beta 2, the effect of being after the time period. It's about that much. All right, so this is what we are assuming for, Tokyo, is that they'd be here, beta 2 higher. All right, now beta 3 is the effect that we are interested in. this is the effect of the makeup extravaganza. It's the effect of being in the treated group after the time period. Right here, ladies and gentlemen, is beta 3. That is the money right there. Okay? So we're after beta 3, and that's our difference in differences. And that's how that works. So we can estimate the effect of having a makeup extravaganza by looking at these two different groups. So remember, but the critical assumption here is parallel trends. San Francisco and Tokyo, we have to have good reason to assume that they would have followed the exact same trend without the makeup extravaganza. Okay, it's difference in differences. Now that's a 2-period difference in differences, but you can write that in a more generalized form. Let's go back to just rewriting our panel model in a bunch of different forms. So this is going to be beta naught plus, and now here's what I'm going to have. Okay, I'm going to have a, what am I even doing right now? I'm going to have a set of dummies. Okay, I'm going back to the fixed effects type thing. I'm going to have a set of dummies for our fixed effects for alpha, right? You remember how fixed effects works. It's just a bunch of dummies, and this is how we determine the individual. Are you this individual or not? Are you this group or not? Okay, so it's the same type of thing. The treated or non-treated, we're just generalizing it. And then we're going to have another set of dummies. This is going to be T set of dummies. Okay, this is what time period you are in. All right, so are you in the we're just going to do it for which time period that you're in. So we're going to have all these dummies for I and all these dummies for T. So we're doing fixed effects here for I and fixed effects here for T. So this is like fixed effects but like 2 ways, right? And then we're going to have the actual, this is delta, the actual effect of treatment that we're interested in. I'll call this SIT. S is just going to be 1 if you are a treated group in a treated time period. Okay, you're in one of the treatment groups and you're in a treated time period. That's when that's going to be 1. That's our interaction term right there. And then plus some error. Okay, don't forget your error. So this is a generalized version of difference in differences, and we call that, ladies and gentlemen, we call that 2-way fixed effects. Okay, generalized version of difference in differences that I've written right there. Okay, and that is how you do that. So that's done. Anything else I want to say about those kinds of things? One thing I did neglect to mention is that fixed effects is often preferred over first differences, all being equal. I mean, over 2 time periods, just 2 time periods, like they're going to give you the exact same result. But fixed effects is preferred because it has a lower variance. The standard errors will be more precise. So just a little factoid for you, but man, panel data, time series data. What's the point, right? Let's go back to cross-sectional. Just for one last hurrah. And Zoe is thinking at this time, okay, look, it's really about, it's not really about number of demons killed per se. What are we thinking about? We are trying to prevent demon invasions. Okay, we just don't want a demon breakout. So what if instead of this linear combination model I've been doing, because what if I wanted a probability model? I'll kind of switch this up, right? I'll call y, I'll make y in the interval 0, 1, okay? So it can be 0, it'll be 1. I'll say it's closer to 1 if we prevent a demon outbreak. So like when y is 0, then there was a demon outbreak. I'm gonna flip-flop this because I like it better. So if y is 0, there was a demon outbreak, and if y is 1, there was not a demon outbreak. So therefore, when we estimate this, it's going to be a probability model, essentially. And we could do a linear probability model. I mean, we could have our y be like that, and have it be just like this linear probability, and go back to our cross-sectional data and do all of that. But you'll see that with a linear probability model, we end up with some regression line that's it's like this, right? And 1 is here and 0 is here. And you see the problem is that with a linear probability model, you can hit probabilities below 0 and above 1 in your prediction, which isn't like ideal, right? What you really would like is to have some kind of model, a nonlinear model that, you know, binds you between 0 and 1, something maybe like that. Okay, kind of looks like a CDF, doesn't it? That's not related to anything we're going to talk about. Okay, so you want some kind of nonlinear model, just like that. Okay, so instead of this linear business, let's see what kind of linear model we can do. We're going to say our model, we're going to model the probability that yi equals 1 given x, right? And we're going to have that be some function of x beta. All right, so what's that function going to be? Well, there's a couple functions that actually work really well for that. Okay, these are our functions. First one is called Probit. What is Probit? Literally, our linking function for Probit is, I'm going to write this here. What does that symbol mean? Okay, that capital phi, I believe, is what that is. And that's just a shorthand we use for the CDF of the standard normal distribution. Okay, so hey, CDFs look a lot like that, don't they? Okay, so we'll just use the CDF of the standard normal distribution, and that's going to model our probability. Perfect. Okay, I love that. Do we need to use Probit? No, there's another one. We can use Logit. Logit is another common one. Kind of looks like Logit because all we're going to do is we're gonna log it. We're going to log that. Log the probability. And I'm not going to. We do have a log form. I'm going to skip that and basically write this in the form that we wanted in, which is going to be e to the x beta over 1 plus e to the x beta. Okay? Now, strictly technically speaking, these are the inverse link functions for Probit and Logit, but like you don't even get into that in 388, so it doesn't even matter. Okay, so for our purposes, that's Probit and Logit. And let's see. Oh, we can use these to model our probability. So our g of x beta, g, we could use this function or we could use this function. Those both work very well. They give you super similar results. All right, and here's how we're going to estimate it. We're going to estimate it with maximum likelihood estimation. How does that work? Well, we have some function. We call that the likelihood function. We're going to choose the arguments, our vector of these, to maximize the likelihood of observing the data set that we got. What function would maximize the likelihood, maximize the probability of observing the data set that we actually have, is what the likelihood function is telling us. And the likelihood function is going to be the product from I equals 1 to n of g of x beta to the, let me make sure that I'm writing this right, g of x beta to the y it times 1 minus g of x beta to the 1 minus y it. That's your likelihood function. Actually, for mathematical reasons, it's better for us to take the log of this likelihood. So we'll take the log of this function and then the product of all these things, because it's log rules, is going to turn into the sum of a bunch of things. Okay. So, and then we're going to maximize the log of that likelihood, and that will be better for us. Okay. That's how we do maximum likelihood estimation. Honestly, after thinking about all this, Zoe goes, you know what? I've realized I have a lot of options, and I can estimate. I can choose a model. I can choose my question. I can choose a bunch of different models, different data sets, different estimation methods. I know how to do inference. I feel like an econometrician. Okay, and that is exactly where we wanted Zoe to be. So honestly, that's where I'm going to end. Okay. If you have any other questions, feel free to like, subscribe, leave a comment, and till next time, proud of you for doing econometrics. Keep it up.